Yeah. Yeah. So suppose in phase means what? If the angle between both the waves is 0 degrees, okay, 0 degrees, then that is said to be in phase. Means best example for this is what I told you yesterday. What is the best example for this? For in phase, what is the best example? Yes, anyone can try this one. What is the best example for in phase? In phase, best example is soldiers marching on a like so soldiers marching. I told you about the RD parade. Yeah, soldiers marching. That is the best example of in phase. Okay, then what is out of phase? This is in phase. What is out of phase? Anyone? Can anyone try what is out of phase?
So when two waves move in opposite directions?
Yeah, if they move in the opposite direction. I mean, like there are two waves which are moving in, like the angle, phase angle is here 180 degrees. Here theta is 180 degrees. Or phase angle is denoted by phi. Phi is 180 degrees. Here phi is 0 degrees. Okay. Then what is constant phase difference? What is constant phase difference? Yes, Abid, Ashaz. What is Abid and Ashaz? What is the phase angle? What is the here? What is the angle between both of them? What is the constant phase difference? I told you yesterday the definition. I have given the definition also. I have sent the pictures also. Everything I am sending now. Constant phase difference means leading or lagging of a wave is known as constant phase difference. Why? Because I am going to use these terms now while doing RLC circuit. If I don't explain RLC circuit, you cannot understand LCR series circuit. That is a problem. Okay, anyways, I will not take much time for this. So once again, quickly. So what is phase? Phase means it describes the state of motion and direction of a particle in phase. In phase means if the angle between both the waves is 0 degrees. Okay, that means if they are exactly in phase, means the angle is 0 degrees. Example for this is what? Soldiers marching on the, like marching, like at the parade. Okay, the second is out of phase. Out of phase means angle between both the waves is 180 degrees. They're completely, that means they are in opposite direction. Constant phase difference means leading or lagging of a wave. Now we will go back to the resistor circuit. Yesterday we have done the resistor circuit. This was the resistor circuit. What happened here? This is a voltage and this is a given voltage and this is the applied voltage and this is the current. The dotted one is applied current. So are they in phase or out of phase? Yes. Are they in phase or out of phase? Yes. In phase or out of phase? These two waves. This is a voltage and this is a current. Are they in phase or out of phase? Yes, Dhruti. Ashas.
Phase.
Yeah, they are in phase. They are in phase. Okay. The voltage and current, they will ask this question in the exam. Okay. Are they in phase or out of phase? Yeah, both are in phase with each other. That means when you apply voltage or potential difference across the resistor, then the current is in phase. Is that clear? Then the current is in phase. Now I'll go with the next one. AC voltage applied to an inductor. So today's topics will be inductor and capacitor. So I'll try to finish off so that I can focus on LCR also. Okay, RL, see, keep that in the mind. RL, RC, LC only qualitative thing is there that I'll explain later. So I'll just go ahead with the LCR series circuit, which is an important one. Okay, there are some more definitions to be discussed over there. Now, so here now so now here suppose an inductor is connected in AC. Okay, keep that in the mind when I'm discussing about AC. That means what? It is connected to a frequency generator or an oscillator. This is a frequency generator or an oscillator. Okay, frequency generator or an oscillator. Okay, now what happens? This is L. This is the inductor. Okay, this is the inductor means simple words. It is a solenoid. When I say inductor, it is a solenoid which stores magnetic energy, in the form of magnetic field. Is that clear? What is the function of an inductor? The function of an inductor is to store magnetic energy in the form of magnetic field. Is that clear? Is that clear, all of you?
Yes, sir.
Yeah. Now, also there is one more function that is used for filtering. The meaning of filtering is what? Here it blocks a DC and allows AC to pass through it. Okay, it blocks DC and allows AC to pass through it. Okay, that means it wants a uniform pulse to pass through it. That's the reason. So now here we have, again we'll go back to the equation. We have V is equal to what? Vm sin omega t. Okay, you can understand why I am taking sin omega t. Okay, now summation E of t is equal to 0 means whatever this is according to the Kirchhoff second law. Now voltage here, so voltage across EMF is V minus, I'm writing V minus L into di by dt. So voltage across the inductor is given by V is equal to what? L into di by dt. Means suppose, see, according to grade 11 first chapter about the physical quantities, you can add or subtract similar physical quantities only. Means what? You can add kilogram to kilogram, you can subtract kilogram to kilogram. Is that clear? We can add liter to liter, you cannot add kg to liter. That is not possible. Same way you can add voltage to voltage, subtract voltage to voltage. Is that clear? So inductor value is L, but we cannot subtract V minus L. That is not possible. So the voltage developed across the inductor is given by L into di by dt. Is that clear? The voltage developed across the inductor is V is equal to L into di by dt. So the voltage across the oscillator is L V and V minus L di by dt. This is using the Kirchhoff second law. Now what I am going to do? I am going to solve it now. I am going to just solve this equation. So what I am doing? So I will get L into di by dt. L into di by dt is V. Okay. L into di by dt is V. Clear? Now after that I am going to solve it. Di by dt is what? Di by dt is equal to V by L. Okay. Di by dt is equal to V by L. What is V? V is equal to Vm sin omega t. Vm sin omega t divided by L. Is that clear? Di by dt is equal to Vm sin omega t dt. Now I am going to differentiate this equation. Means what? Di by dt into dt is equal to what? Vm into sin omega t, Vm sin omega t by L into dt. Is that clear now? Is this clear? These steps are clear with you all?
Yes, sir.
Ashas, Abid, is this clear?
Yes, sir.
See, once again, see, we started with this is the input function. This is the input voltage, what I am giving to the inductor. So this is according to the Kirchhoff law. So the same Kirchhoff law I applied here. This minus this should be equal to 0, or this should be equal to this. That is the meaning of that. So I got here what? V is equal to L into di by dt. Cross multiply, you get that one. So now apply dt on both the sides. Differentiate it. So what will happen? This and this will go away. Only I will be remaining. Okay, I is equal to what? I will be equal to, I will differentiate this also. So what will happen when you sin is minus cos, or we are applying integration actually, not differentiation. We are applying integration here. Okay, we are applying integration. What is integration? Integration of sin x dx equal to what? Minus cos x plus c. Minus cos x plus c. This is the formula. Okay, integration of sin x dx is equal to minus cos x dx. Okay, so minus cos x dx.
So how did we get this?
Yeah, this is the integration formula. What I am doing is I want to find out. See, I am integrating this. I am integrating this. Okay, is that clear? Or I will write this step separate.
Yes, sir.
I'll write this separately again. So di by dt is equal to what? Vm sin omega t divided by L. Okay, Vm sin omega t divided by L. Now what will happen? Now integrate on both the sides. When you are integrating, see, integration dt with respect to dt. Like while differentiating, also we are differentiating with some term. Here I'm integrating with respect to dt. Here also I'm integrating with respect to dt. Why I am integrating? If I want to find out the entire value, I have to use integration. Okay, if I want to find out the rate of change, then you have to differentiate it. What is happening now? Sin x integration is minus cos x. Now when you integrate it, what will happen? Integration of di by dt will become I. This whole thing will become I. So it is equal to what? Vm by L. Okay, we will remain with what? Vm by L. Sin x integration is what? Minus sin omega t is minus cos omega t. Minus cos omega t. Omega t integrate derivation is what? Omega. Omega t derivation is omega plus constant. Plus constant R. Some constant. Is this clear up to here? Is this clear? So
Yes, sir.
yeah. So what is that? Constant is independent of dimension of current and independent of time. Okay. So it has dimension of current independent of time. So the constant here is having, this constant is having dimensions of current, and independent of time. Dimensions of current and independent of time. This generally this is said to be integration constant. When we are writing this, when you are doing indefinite integrations, like second book first chapter, we have integrations. So this is indefinite integrations. In that case, we have C. Now I is equal to what? Minus Vm by L cos omega t by omega plus constant. Constant is having a dimension of current and independent of time. Now what we are writing? Minus cos omega t. How can we write minus cos omega t? See here. See, we'll just go ahead. So what is that? Cos theta is equal to what? Sin 90 minus theta. Is it not? Sin 90 minus theta is minus cos. Sorry, sin yeah, minus cos omega t or sin theta minus pi by 2. Okay, so here I'll write here minus cos theta. Sin theta, sin 90 minus theta, sin 90 minus theta is equal to minus cos theta. So now, so here we have what? This is what? I is equal to what? Vm by omega L cos omega t you get. Okay, so we are writing here I is equal to what? I is equal to Im sin omega t minus pi by 2. I is equal to Im minus pi by 2. So I is equal to Im is equal to what? Im is equal to Vm by omega into L. See here, Vm by omega into L is in the denominator. That is nothing but what? I is equal to minus Im cos omega t. Okay, but that can be written as what? Sin omega t minus pi by 2. Is that clear now? So I'm writing here. That is why I wrote there sin omega t minus pi by 2. See once again. This is I is equal to, from the previous equation we got minus Vm by omega L into cos omega t. But I don't want this cos fellow, because when I have sine with that, I want to compare with sine only. I don't want to compare with cos. Understood now? When I am having input as sine, I want to compare with sine only. I don't want to compare with cos. So for that, I want to convert cos into sine. So what is the way of converting cos into sine? So I just write sine omega t minus pi by 2. So this in the place of this, I'm writing sine omega t minus pi by 2. So what is Vm by omega L? That is Im. Is that clear? Is that clear, all of you?
Yes, sir. Sir, here the constant is
Yes.
pi by 2.
Here the constant is pi by 2. Okay. Here the constant here we can take it as pi by 2.
Okay, sir.
No, that is not. I mean that is a having dimensions of current. See, I am just converting cos into sine. What is the way of converting? See, sine 90 minus theta is cos theta. You know that, no?
Yeah.
I am doing in that way, not the constant thing. Constant you leave it. Constant is having the dimension of current. That's a
Okay,
different
sir.
thing. I mean, I want to convert Sine 90 minus theta is what in simple words?
Cos
Cos
theta.
theta, that you know, right? Sine 90 minus theta is cos theta. I'm applying the same thing here. Is that clear?
Yes, sir, got it.
Yeah. So now what happened here? Also, omega L is what? Omega L is said to be inductive reactance here. Omega L is said to be inductive reactance. What do you mean by reactance now? What do you mean by reactance? Reactance. Reactance is also known as impulse response. In simple words, I will tell you. That is said to be impulse response. Impulse response. Okay, we'll go to some biological term. Like someone will poke you with the pin on your skin. What will happen? Someone,
It will start bleeding.
yeah,
It will start bleeding.
no, he just pokes like little, touches with the pin. You respond, right? You respond it. Just move your hand, right? Is it not?
Yes, sir.
Suppose something is coming very close, a fly is coming or a mosquito is coming very close to the eye. What will happen? What do? You just close your eyes, right?
Yes, sir.
So that is an impulse response. Is that clear? When something is happening, so it is an impulse response. Like suppose a ball is coming towards you very fast, so you just move from there, right? Is it not?
Yes, sir.
So that is said to be response, impulse response. That means where the body or the mind is responding to the situation. That is impulse response. Now, what happened is when I'm because see, I can compare resistance to resistor again. As I told you, similar physical quantities can be added or subtracted. When I'm comparing current with I have to current I have to compare, voltage to voltage I have to compare, resistance to resistance I have to compare. Now what happened is I have a resist. I have to compare with the resistance now. This inductor. So what I am doing is the inductor is also having impulse response, or that is said to be reactance. Means what happens when you apply the potential difference across the inductor, it doesn't mean that immediately, oh, okay, come here, you can go. Suppose someone comes to your door and he wants to trespass. Will you allow that? You won't allow, right? You'll just check first who is it, right? You'll peep through the hole and you'll just check who is the person. If he's your relative or if you know the person, then you'll allow in your home. Is it not? So
Yes.
so the same thing happens in the inductor also. Inductor, what happens in the beginning, it will resist the flow of current. When you apply the potential difference across the inductor, initially it opposes the flow of current. So that is why inductor, which is fitted in the tube lights, in the old tube lights, not the new tube lights, in the old one. Nowadays we have LED tube lights. That's a different thing. In the old tube lights, it used to flicker. The tube light used to flicker. You know that? Have you seen that one? Yes, Abid, Ashaz, you are not responding. The old tube lights, suppose if you switch on the tube light, it will flicker for 1 or 2 times. Is it not?
Yeah. Yes, sir.
Yeah, Dhruti.
Yes, sir.
Yeah, did you see those tube lights like flickering like 1 or 2 times it will
Yes,
flicker and
sir.
then it will switch on? Did you notice that?
Yes, sir.
Yeah.
Yeah.
So same thing. Why? Because the tube light doesn't allow, like it's acting like a filter also. So what is happening? It started opposing in the beginning. Then what happened when the signal came properly? Then it allowed. Is that clear? So what happens is that impulse response is named as reactance. Opposing is known as resistance. So in the other words, for inductor we don't say inductor resistance. Instead of saying inductor resistance, we are saying inductor reactance. Is that clear? So we are saying inductance reactance or inductor reactance. So this omega L is known as inductor reactance, which is denoted by XL. Okay, which is denoted by XL. X suffix L is known as omega L. Is this clear? This concept, all of you. Is this concept clear?
Yes, sir.
Yes, sir.
Yeah. Now what happened here? So XL is directly proportional to that. Means if you remove omega, so we can write here XL is directly proportional to L and XL is directly proportional to omega. Okay, is directly proportional to omega, the frequency. I will write mu here. Is directly proportional to the frequency because omega L is there. Means the inductive reactance is directly proportional to the value of the inductor. More the inductance value, more will be the reactance. More it will react. Means more will be the resistance. And the more is the frequency, more it will react to that one. That means resistance also will be more. Okay. So here what happened when I was converting? Now one more thing, if you notice here, when I was converting my cos to sine, I got into picture. What is it? Pi by 2 came into the picture. Means what? Here current here minus is also there. Means what? When I'm applying voltage, current lags by how much? 90 degrees. Is that clear? Did you understand why I was teaching in phase, out of phase, and constant phase difference?
Yes, sir.
So here there is a constant phase difference. What is a constant phase difference? Who is lagging? Current is lagging. Voltage has the same signal. There is no change in the voltage signal. Who is lagging? Current is lagging. Current is lagging by pi by 2. Means when see I have to start my class 10 a.m. I started my class at 10 a.m. But students join 10:05. Example. 10:05 means they have lagged. Okay, so that means I started. The bus has to start 8 a.m. from the place. What happened? There is a lagging. So what happened? Every time there is a lag. How much? 5 minutes lagging is taking place. Understood now? Means the bus will reach the stop every time 5 minutes late. Understood now?
Yes, sir.
That is said to be lagging. How much lagging took place? 90-degree lagging is taking place. So I will draw the waveform for you. Then I will also draw the phasor diagram for you. Is that clear? So once again from the beginning, see here, this is a, I didn't write the, okay. So I have tried the heading, I forgot. Okay, inductor, AC applied across the inductor. Okay, AC voltage applied across, AC voltage applied to an inductor. Now, now what happens is an inductor and this is a AC. So what happened? We are applying a frequency. This is a frequency generator on or an oscillator. So it produces a signal and it reaches the inductor. So what happens? The voltage across the oscillator is given by V is equal to Vm sin omega t. This is the principle of what Kirchhoff law. Then we apply the Kirchhoff law for this. The voltage applied across the inductor is V is equal to L into di by dt. Just simplify this, you will get this one. Then after that, what is V? Vm sin omega t. Integrate it on both the sides to remove the di by dt. I don't want the di rate of change. I don't want. I want current, not the rate of change of current. So for that, I'm integrating it. When I integrate it, I got I here. I got Vm by L that I got it here. Sin omega t is minus cos omega t by omega plus constant. Constant is having dimensions of current and independent of time. Now, we XL is proportional to X is proportional to nu. Means it is directly proportional to the inductor and also directly proportional to the frequency. Okay, so minus cos omega t. So if I want to convert cos omega t to sin omega, sin omega t to, sorry, I got cos. I want to convert it to sin. So here I got cos. I want to convert it to sin because how do I can compare easily with sin again. So sin 90 minus theta is minus cos theta. So cos theta actually. So then I got here Im sin omega t minus pi by 2. So what is Im? Vm by xl. So omega L is what? Inductive reactance, or it is also known as impulse response. So what is xl? Xl is equal to omega L. Okay, xl is said to be inductive reactance. So xl is directly proportional to the, this is important, it's directly proportional to the inductance and also directly proportional to the frequency. More the frequency, more will be the inductive reactance. More is the inductor value, more will be the inductive reactance. Is it clear all of you?
Sir, I have a doubt.
Yeah, tell me.
Inductance reactance is XL or WL?
Both are same. In the place of omega L, we are writing XL. Understood now?
Oh, basically
This
it's a
is written like this.
representation.
Same only. We are writing Im is equal to Vm by XL now. Is that clear?
Yeah.
It's the
Okay.
same. Vm by XL we are writing. Is that clear now? So
Yes, sir. Yeah.
okay, right. Note down this value. Okay, I'll just take a picture and send it to you. You can copy. Then I will also explain you now the thing. Okay, 1 second. Okay, now going ahead now. Is it clear? Can I go ahead now with the next
Yes,
one?
sir.
Okay, the waveform I will explain now. I am going little slow because I want to make you clear with these terms. Okay, now I'll go with the waveform, then I will go with the phasor diagram. That's enough, so that we can again go with the what exactly happens in the steps. Also, I'll explain that also. Just 1 minute, I will have some water and come. Now, now here, now. So if you draw the here, we can. I'm writing here. Current lags the voltage. Current lags the voltage by pi by 2 or 90 degrees. Okay, pi by 2 or 90 degrees. Means what? 90 degrees means 1 by 4th cycle. 1 by 4th cycle. Clear? It lags voltage by 1 by 4th of the cycle. Now, what is happening? See, we'll see the waveform, how it is. Now, see here, look at the waveform. This is my input cycle. Okay, this is Vm sin omega t. This is V. So, current is lagging. So, how much it is lagging? 90 degrees. See here. See here, it became maximum. Now, again, it started coming down. Is that clear now? Is this clear all of you? When it is down here, it came like this. So, it came in this way. Not with that. This whole thing is not. Is it clear? The dotted line, I'm just making it darker. Suppose if there is a red pen or something, I would have drawn that. But okay, is this clear? So this one is the current. Okay, the current is lagging the voltage by how much? 90 degrees. Is that clear? One is replying. Is it clear?
Yes, sir.
Ashaz and Abid. Ashaz Abid. Is it clear?
Yes, sir.
Ah, reply, man. If you don't reply, how will I come to know? Okay, first of all, you're online. Number two, all our cameras are off. Okay, as a teacher, I am telling you, what happens in the class, I will tell you. Suppose we ask a question and we'll try with the expressions, we'll come to know. With the expressions of the child, we'll easily come to know whether the child is understanding or not. No need to even tell whether I did not understand or I did not follow. Easily, a teacher can easily understand that, yeah, the child might not have understood. Then immediately he or she starts explaining again. Okay, so first of all, we are online, and also all the cameras are off. At least reply to the questions. Okay, so it will be easy. So it's like it is encouraging for the teacher. Now, now here we have a phasor diagram. How is the phasor diagram? Let us draw the phasor diagram. So this is the phasor diagram. Now, so this is the